Hi, let's discuss another problem in this chapter 2 about sequential systems. We are at the very beginning, so it's a good idea now to discuss how the flip-flops work when connected together in some kind of network, right? In the same way that we started the course CSD, when we connect together several gates of different kinds, And what was the purpose then? Well, it was about analyzing the circuit that was invented. So you had to organize a goal, you had to plan the project or the problem, and then you had to discuss several different methods so that you can reach the solution in the end. So this time is, pretty much the same thing. You are starting a new chapter, and now you have, in addition to the classical gates that you know from P1, from the chapter 1, now you've got something else, which is the 1-bit memory cells, especially the ones which are synchronous and capable of running by means of a clock signal. For example, the rising edge from a clock signal. So this is the purpose, for example, of this recording today. Let's discuss on asynchronous circuits, because if you have some flip-flops in your hand and on the table in your lab, you can connect them the way you like. For example, in this way, you can consider several flip-flops, GK, and one of them with the GK connected together. So indeed, this is it's nothing but a T flip-flop, right? So you can use some gates here to connect outputs to inputs in any way you like, right? So the point is this one, the objective is analyze this kind of a synchronous circuit, all right? And try to discuss which are their main drawbacks, okay? Why we are not going to follow this line of designing like this in this ordered way, you may say so, right? Why we will switch to a standard and canonical finite stage machines where every single flip-flop is run, by means of a synchronous clock. So why all this discussion here? That's the point. All right. So this, when you have a chip, naturally, a 1-bit memory cell, you can as well go and see what happens on how it's going to look like the data sheet of a commercial chip of that kind. For example, the 4027, that's the classical chip in CMOS technology, which is nothing but a GK type flip-flop that you can use. It's a dual GK type flip-flop, so you can use it to organize any kind of circuit, okay? And naturally here, everything that we have to go through is invented and is dislocated in the digsys web. So for example, why not take one of the problems in this problem collection, the problem 5.4, for example, which is the picture that you see here. So the goal is how the circuit works, right? Well, so it's, even if it's an analysis circuit, I like to organize this in the usual way, Let's talk about the specifications and planning, and then let's see what else we can do to solve the project. Okay, because in the end, solving the project will be, getting the timing diagram, so we can see how it works in time and what is looking like the circuit and which is the purpose of the circuit and if it can be used for anything else or for something, right? So this is the specifications. Then you have the planning. But a circuit like this is not simple, especially if you are beginning with this business. It's not simple. You have 3 flip-flops connected in a weird way. So let's go step by step. Take it easy, right? That's my method, Let's do it step by step. For example, do you know what is exactly a GK flip-flop? Because this is the purpose of the P5 project. Specifically, design a GK flip-flop from the very beginning to the end. So you have the component. So that's very important, You have the component. And once you've got the component to the end in the usual way by means of VHDL design, you can use it, for example, here, right? Organizing this structure. So once you've got the GK flip-flop studied, you can go and ask yourself, do I know something about connecting two flip-flops together? Like this, you see, this is quite weird because you have one clock here in the chip 1. In one hand you have one clock, but then the next flip-flops, you see, the chip 2 and the chip 3 has the same clock, but it is not the clock from the chip 1, but is derived from the Q naught of the chip 1. So you see, this is the definition of a synchronicity. You have several clocks, which is going to make the things very complicated and unreliable at all in the end. So, you know, if this is your situation, if this is the first time that you go through these kind of examples, why don't you pay attention and solve first a simpler circuit, like one which is based only in two flip-flops? How to connect two flip-flops and see what you can do with two flip-flops. And when you get some experience on this, you can reach the final goal, which is, you know, finding the timing diagram of the full picture, which is, for example, this example, which is the problem 5.4, but you've got in the collection many more, the 5.9, the 5.8, you know, several of them, and all of them thought in the same way. You have on the table several flip-flops and gates, and you connect them in any way. So it's just a kind of drilling exercise to get used to signals and clear directs and ones and zeros and clocks and the like, right? So that's the point. But you know, the next step is this time different, because this is an analysis. You don't have to design anything here, because the circuit in the end is given to you. So you have, for example, why not 3 methods, right? The typical method and the most direct one is to try to solve the circuit in paper. You know, you take some sheets of paper and a pen and a ruler, and you try to organize a timing diagram. Why not? First one flip-flop, then 2 flip-flops asynchronously, and finally the final circuit. That's one way, and you, in the end, you will get a timing diagram. Another way, because the circuit is already solved, you know, another very interesting way is try to mount, as if you were in the lab, the circuit. This is why you've got SPICE simulators, you know. Every flip-flop is modeled in some way or another, so you can pick up the model of these devices and capture the circuit. As in the P1, you know, you captured the circuit and you switch the play button, and then you get what you wanted. And that case was the truth table, and now is going to be a timing diagram, for example, by means of a logic analyzer instrument. Okay, you have several possibilities here. Naturally, there are many SPICE simulators, virtual labs indeed, all right, that ones that you take home. So one of them is Proteus, you know, the usual one that we use all the time. And then you've got as well multisim. Multisim is available to you. It's licensed by the university, so you can download the multisim in your computer and you can get the license from your lecturer, right? It's very simple. So it is a full featured, you know, SPICE simulator that can handle very well a circuit like this. There is no problem. All right. So you can see the waveforms just like that in the screen or an oscilloscope or a logic analyzer. And you know, the third method, and our favorite one, is the VHDL. Because the circuit exists and everything is connected, the only thing that you have to do is to redraw it, you know, annotating every single wire, you know, specifying every single component. So here you have a project of 2 files. The top one, which is this circuit that you may call a sync circuit, for example. And then there is a component here that can be used, GK flip-flop, and annotating every signal. So that's the third method, right? So you can develop a project in VHDL as usual. So you can synthesize the project for a given target chip. So you can inspect the circuits in the RTL view or technology view. And finally, you can reach the functional simulation, which is going to be pretty much the logic analyzer that you've got in Proteus or Multisim, or the timing diagram that you got in paper, right? And finally, the advantage of this VHDL method is that it's very, very precise, So you can continue from the functional simulation to the gate level. So you can continue the testing at this gate level, so you can get specific things or specific features and drawbacks of this kind of connections, the asynchronous circuits. For example, you can detect glitches and unknown or unwanted codes in the outputs, and which is the maximum frequency of operation as usual, So in the end, you've got the project solved in 3 different ways. It perhaps is going to take time, but this is the big panorama, right? This is the big picture, and it's presenting you all the possibilities that you have, to organize your final discussion and reporting. So you see, in the end, and this is, only one of the projects that you've got listed in the problem collection. So almost, this is a kind of an example, and can be repeated for many of them the same way, right? So let's just start to see where is everything here. For this is digsys, this is P5, right? And at the same time, you can just get another window, and this time home, and the problem collection, which is here, PDF. So you've got the problem collection, right? So if you find the problem 5.4, it is that like that, you get it very fast. So this is what you have in mind, that this is written in this way, right? Like a long project. A, B, C, D, E, F, G, and the like, You can even connect in the G section this device, this circuit with perhaps a better version that you can get if you follow canonical finite state machine, which is not bad, right? So the idea is always the same. You have an invention here. This invention is going to be for something. So is there a way to get the same circuit better and more systematic than this, weird way to connect synchronously the flip-flops? So probably yes, but this is going to be left for the next P6, right? So in P5, you know that you've got the flip-flops. Precisely, the P5 itself is the GK flip-flop design, okay? So that's the starting point. You have to be able to get the waveforms, for the Q waveform from driving signals like those ones that you see here in this picture. This has to be understandable and comprehensible to you, right? So you have to spend some time trying to mimic this picture in a sheet of paper, right? Applying the clock, and then the clear direct pulse, and then drive some G or some key and see what happens in the time when you've got this rising edge in the clock. So you have to follow the function table and see which is going to be, annotate down there, the Q, which is going to be the Q in time. One clock after the other, because this is the basic flip-flop. All right. So this flip-flop, it is like that. It works following, you can design it very well following the finite state machine strategy, as it is pointed here in the planning section. So this is yet another example where to apply a simple finite state machine. So you can develop this project, right? So in the end, you will generate a kind of GK flip-flop file, and finally you can just test it with this picture in mind. Now you write two processes for inputting the signals to the unit and the test. Okay, one process for inputting the GK and clear direct pulses, for example, and data, and another process, you can do it like that, and another process that goes concurrently with the other one. So the other process is for injecting the clock signal to the circuit, right? And finally you can go and monitor the input and outputs. So this picture is going to be solved once and again for the many circuits ahead right now, right? And finally you go and write the report. So this is, for example, one way to start the problem. All right, this is what I recommend you. In this way you go back and get in touch with, for example, the VHDL tools. Another way to do that is to go and run some example, in Proteus, for example. Run the problem immediately in Proteus, taking one example from the collection of Proteus problems, all right, and try to do the same thing. Perhaps it's faster, okay, because I gave you many times examples of circuits that can be immediately fixed in Proteus, so that's a good way to go through, right? From you can get that from the problem itself, I think. All right, for example, here you see the section F. It is like that. It is like the second method that we lay out in the presentation. Okay, so you can go and modify the problem 5.8 to become the problem that you are studying here. All right, so if you click here, you will open the Proteus example, and you can start, for example, from this point. Well, if you already know a little bit about the waveforms, because what is the point of getting waveforms that you know from you don't know how to interpret, right? So if in Proteus you've got a circuit like this, which works, you see, first of all, you can click the play to see if it is going to work or not, So let's see if it is going to work. You click you trigger the device, and you see waveform, right? So this is an asynchronous circuit, so your circuit, the one in the problem 5.4, is not going to be that different from this one. So now it's a good time to stop the simulation of these and start modifying it in a way that is going to resemble in the end the one that you have in mind. So now it's time for go and editing this. For example, this one can be deleted. Okay, you make room for Q0, Q1, and Q2, chip 1, chip 2, and chip 3. One of the flip-flop that you've got here is not the T, but the GK, so you can copy this up there, and you can replace that one, You can go to the child sheet. Well, you can go to the child sheet, yes. You can mark it all. You can save it into the clipboard. So now is the good time to change the name. For example, GK flip-flop, right? So now you go and again to the child sheet and paste from the clipboard, and now you've got the chip which may be modified very well like this, G, and you copy this terminal. Another one, this one is going to be, well, right, you can copy this one here. This one is going to be J, the other one K. You see, you can take as a basics the 4027, the standard chip. So it is something like this. You can disable all the time the set direct, but you can convert the clear direct as a terminal as well. So this chip is going to be your GK flip-flop now, right? So you can make it as usual. So you can copy two terminals here. One of them is going to be key and the other J. That's the circuit. If you like, you can add as well here, in case you would like to use this for other projects, another terminal which is the Q0. Why not? Because you can copy it. Is already here, you see, Q naught. Okay, the Q naught, which came straight from the chip. So the Q naught goes as a terminal if necessary, right? Well, in this example, it is true. You have to use it. So this is going to be your chip now. So it's time to get rid of the other chip. Well, let's leave it at least one of them. Okay. Let's set aside. For example, the one which is really a T flip-flop is the chip 2. The chip 2 is a T flip-flop because there is no difference, right, between a GK with a key and the J connected together, and this is the same as the T. So the chip 2 is nothing but a T flip-flop, right? So now you can go and connect the clear direct. Well, let's finish with this. Let's make some room. Okay. So now you can copy these 2 times, one time here and another time there, right? This is going to be the chip 1, sorry. This is going to be the chip 2 and this is the chip 3. And this cannot be the chip 1 again, right? Because you've got one of them. So this is going to be the chip 5, for example, whatever. And now it's time for connecting something like this. VCC here at the K input with the chip 1. Now you need an inverter, and you know that the inverter is from the technology that you have in mind, which is the CMOS 4000 series. The inverter is the 4069, right? That one. So you take it to your, this is like going to the lab drawer and take it and put it on the table and use it, right? You can make this thing text field out of here. So now it's time to flip this, mirror, X. Now you can continue with the connections. Okay, you have another VCC to connect here, which is this K. The T goes connected to the J. You can connect all the clear directs. And now it's time for organizing the clock, which is going to be like this. Be aware of the labels, right? You need a label to this clock. So place a white label. So this is going to be the label clock. And this is going to be the label CD. This is because you are using the labels down there, right? So if you signal now, for example, this highlight the net, you see it is in red. All what is called CD, it is like that in red, right? So now what is left is finalizing with the clocks. You see you have 2 clocks here. One clock that is the Q naught from the chip 1, and another clock which is the one that you are going to drive by means of a function generator. So now what is left here I see is basically the output. So you connect this to the bus. Okay, this T has to have as well the Q naught, I see. So you copy this and you rename it QL, and now you connect that to the bus. And now you go to the child sheet naturally, and well, the child sheet has already this, so very good. So this is the T, you see, the GK connected at the same T. And now the last one, which is this Q, is Q3. So now the most important thing now for you is to place the label, because you know the full boost is Q3 down to 0 or 2 down to 0. So you edit the properties of this label, do it 2 down to 0. And now this is the same Q, edit properties, 2 down to 0. The Q3 is out of here, so now it is this wire, you know, you have to place a wire label, which is Q0, right? You can pick up it from the list. Another one here, which is Q1, and finally another one here, which is Q2, you know, but you can edit very well the labels as well, horizontally or vertically. This is vertical, so you can edit the label, so horizontal as a rotation like this, you know. The most important thing is that the system recognizes that this is the same wire, you see. So that's the circuit. So this is like going to the lab and mounting the circuit there in a proto board. This is the meaning of this simulation, right? What you can do now? Well, use the instrumentation in the bench. For example, a logic analyzer where you are going to use 5 digital inputs to represent digital signals. So now you can save this naturally because you've downloaded this file from the web. So now it's time to save it in the right place. So you can save the project as in the right extensions. You know, this is going to be problem 5.4, for example, not point but underscore, and this is better placed in your L, right? L CSD, get P5, and now you can generate a new folder which is going to be P for 5, for example, 5_4. So here is a good place to save this file, and you've got it. You need. Now it's time for running the simulation. So you have the instrumentation system here, a simple logic analyzer, and now will you see it is triggered when the CD goes from high to low. All right, because before this edge, this falling edge, nothing exists, or you know that is 0, the output is 0, and you say armed. So you've got the signals, right? So you've got no signals at all. You simply see no outputs here in any way. So it looks like that the circuit is for nothing, but perhaps there is a mistake here somewhere, or you have forgot to annotate it all. So you go and say global annotator. You annotate totally the whole design. Let's see if it is this thing. And now you can rerun the simulation and arm the circuit. And now, yes, you see, sometimes when you copy and paste, you have to go through a global annotation, right? So this is how the circuit works. All right, like this, you see, it is activity in some pulses, you see. Let's focus your attention here larger. So look at this. The system is starting at this falling edge of the clear direct signal. Now the system exists, and you've got, this is the Q0, so Q0 is a kind of a square frequency, but only 2 pulses, you see. And then the Q1 is just another pulse. It goes down for two periods, and then the Q3, the Q2, you know, is low all the time and then go high, and in the end the circuit does nothing else. Right, that's the solution. So this is now your time. You see, in 15 minutes you've got the result. But this is just one way to get results. Now you can copy this into your report, and this can be used as a check-in system, you know. You can check your manual analysis and your VHDL analysis to see if in the end you have the same result, okay? This logic analyzer do not allow you to do many more things apart from just having a marker here. You cannot do a lot of things. So this is why the logic analyzers from the VHDL systems are 1,000 times better than this one, for example, right? If you are solving this in the other one, multisim, probably you have more possibilities because the instrument that you can pick up is the Tektronix that you have on the Agilent or Keysight that you've got in the bench in the lab. And that is going to make you you are going to have more tools to go and see what happens here. This is a very limited logic analyzer, but you know, this time is enough for you for having a good idea of what you are going to expect. All right? Okay, so you've been solving this in Proteus or multisim, SPICE-like modeling. If you want to do the same in VHDL, well, you know that you cannot rush here. You know that you need a plan. And if you pay attention to this given circuit, right, this one here, this is the given circuit, you see that it's okay, it's pretty finished, but it is not finished to the end because some signals has no name. For example, this one here, connecting the Q from the chip 2 to the J of the chip 3 has no name. So what goes now is for you to redraw the schematic and annotate everything and name it all. For example, this signal is going to be W2, for example, whatever the name, but something, right? W2. And the same way with everything, even the signals that are not connected to anywhere. All right? So you have to have this schematic very well annotated, and then you need to find the components, for example, from digsys web. In some way or another, you will find them. All right? So before developing in VHDL, you have to have a plan like this, which is the circuit that you have in mind and now modified with some annotations for every signal. Okay? You can still have the same circuit that you've got in Proteus, for example, deleting the key and making this just a T flip-flop, so you know the signal was not necessary because this was a T. All right, so you can change that flip-flop for the T that you had in Proteus. So now you can mark that like that. So this is going to be the T. Okay, and this is the T flip-flop. All right, so for example, this is the signal W, and this is connected to anywhere but has a name, B3, and so on, right? So you give every signal a name, okay? That's one way to go before starting the development. So now you only have to get the components and the signals to organize the top entity, which is going to be this design, right? So now, accordingly to the plan, you better go to P5 and get the component, right? For example, the GK flip-flop, which is here, save it, save the link as in the right folder where you have to develop the project. So L, CSD, P5, and that one, save it like that, and then you can find, this is the GK, you can find the T in the other tutorial, T flip-flop. So go down to the development section of this tutorial and save this T flip-flop VHD, save the link as in the same place, so you've got them both, and now the only thing that you need is to copy from somewhere else top example that you can modify conveniently to become this one. So where is that you are going to find a top example like this? Well, for example, in P5, you know that the P5 has a lot of learning materials. Well, anything from the chapter 1 is okay, but you can go to the learning materials here as well and go to the asynchronous circuit, because what we are doing now is an asynchronous, circuit. So here you are something similar to study as well. This was a 4-bit binary counter, and it was something like this. And this is a tutorial, so this is fully developed, right? So you need to find something like this. So you go down to the development section, and this one is the one that you are looking for. So you can save the link as, and now it's time to change the name. For example, problem 5.4, right? Like this. So this is going to be your circuit. So you've got from the web everything. Something in, the plan C2 to copy and adapt, and then the two components that you have in your design. So now is your time to go to Quartus Prime and start in the usual way, the organization of the project, and to the end, the synthesis. So I will do that now. So, okay, next, and in the end you will find the synthesis results. Okay, you can just slightly edit and give the entity the right name, problem 5.4, for example, and the architecture may be something like hierarchical architecture plan C2 of this problem 5.4, and this slightly editing allows you to go and start a project and then make the modifications there in Quartus 2, in Quartus Prime, right? Or here, you can continue the editing here with no problem at all. In one hand, you have the schema, and in the other hand, you have the VHDL translation. So this is what we are going to do, but in this case, from the Quartus Prime environment, right? So I will switch off this file, and I will go to the Quartus and ask for add all the 3 files now, right? T flip-flop, problem 5.4. So say next. So let's pick up the cyclone as usual, 115 F29 C7. Next. The simulation tool is going to be as usual, and the language VHDL. Next. And so finish. So now you know that the project is not completed. You have the components, but not the fully edition of the top. So that is what I'm going to do now. All right, I will go to the project. To the project system. And this is the problem 5.4, clock, clear direct, and Q. So this is not the right, well, Q, yes, it's 2 down to 0. Okay. It is Q down to 0. And then, you can go naming the components. One component is the T flip-flop. The other component is the one that you have here as the GK flip-flop. All right. So you can copy this device very well. It's from P5. That way, 2 components, okay? And then some signals. And the signals is not simply the key, but now is when you have to go and keep an eye on your schema. The schema was this one. So you have many signals here. B1, B2, W2. You can think about them as individual wires. B1, B2, W2, B3, for example. Why not? You see B3, W2, B1, and W1 the same, okay? So they are standard logic signals. And now it's time for instantiating this schema. So I will go to the end instantiating this schema. Okay, you go modifying the entity, adding the QL and well, whatever. For example, you have to be aware here because what we have in mind is using two components just to see the variety in which you can organize this. For example, you have the chip 1 and the chip 3, which are GK flip-flops. And when you go to the web, right in digsys, what you see is that this device has a single Q, right? So in some way, you have to modify the architecture in this device. But the one that you've got here in the end, the one that you've been copying already has the QL. So this is good for you, right? The QL is already here. And this is because you have a kind of a signal here, a W. So you have to do the same, for example, for the other one, which is the T that you like to use here. The T has the same idea, Q and Q not. And perhaps the one that you get from the tutorial do not have this signal. So it's your turn to modify not only the big one, the big picture, the top entity or the top circuit, but as well the component. In this way, slightly, let's add this complementary signal Q naught. And how you do that? Well, you can go to the tutorial on the T flip-flop, which is here, the T flip-flop. And you see, this one is without the Q naught, and the full design of this device is without this Q naught. So you go down, and when you see the planning, you have to copy this, because this is the internal schematic of this T flip-flop. And you have to go and slightly modify this picture. So I will capture it and I will do this work of modifying this picture now. Okay, this is the picture of the architecture of the T flip-flop. And now what you need is to add here a couple of buffers, For example, a buffer for generating the output Q, and then another buffer or not for generating the QL outputs. And for example, this wire is going to be called W, right? So this is a slight modification in the picture of the architecture, the finite state machine architecture of the T flip-flop. So now the one that you are going to use has a clock, a clear direct, the T and the Q and the QL. Exactly the one that you need in the experiment that you are organizing, right? So that's the point. So now that you know what you have to do with the T flip-flop, you add the QL, and down here you see you have the signal current state and next state and the signal W, now standard logic, right? And now you can go through this because the CC2, instead of generating directly the Q, now generates the W. And in the end, you need the buffer and the not, you see? That's the way. So now you've been modifying the component this way. There's no need to generate a full project for this small change. So you can go back to your top entity, and now your top entity has to be like that, right? Q, 2 down to 0, the T modified, you see? For adding the QL, which was not there in the tutorial. The GK already had the QL, so now you have to add all the signals in the schema and finally instantiate every single chip. For example, the GK, chip 1, the T flip-flop, you see, and the QL goes to the V2 signal. The QL from this chip 2 goes to the V2, that way, right? And that for every single internal name from the component and the external signal or port. And the chip 3 the same thing, okay? So now you only have to add down here the additional buffers. For example, you have to say that the Q2 is something like what? What is what you see here that is Q2? Q2 is the W3, that way. Then what? Q1 happens to be a buffer for the V2. Okay, and then the Q0 is a buffer for W1. That way. Exactly. So practically everything is here. So that one can be deleted. And then there is nothing else, right? Left. So now that everything has been annotated correctly, you have the top architecture. Okay, for example, here you see a column which is missing. If you don't see this here, now you will see it because it's going to be an error in the analysis. You see, if you left now this W3 without the semicolon, you will find an error, and this is easy to detect. So chip 3, GK, chip 2, T flip-flop, chip 1, GK, and then some logic, which is the 3 buffers that you've got here. And well, there is something missing. You're right. It is the not. P1 is not W3. So you see, in the end, you have to go and give a final inspection to the circuit so that you leave nothing here, like, or the minimum things possible. So P1, this wire is not W3. All right, where W3 is nothing but a signal, okay, that is connected to the output Q of the chip 3. See, exactly. The same one that is buffered to be the Q2. So that is now practically solved. So you can switch off this file, and now is your turn to synthesize it all. All right. So when you finish the synthesis process, you have here, you can inspect here now that you have 3 registers. That's a good thing to notice now, because you have 3 flip-flops in this design. So this means 3 registers that are perfectly well identified. Okay, 5 pins, and well, the logic elements is not that important, but the number of registers, yes, because they have to be clearly identified. So what goes next now is to inspect, for example, the RTL viewer, and it's going to be something like that. Well, right, you see, it is not exactly as you have planned in the picture, in your schema, but now, well, what is left perhaps is to try to see if this is going to work or not, as you have obtained from Proteus, right? So it is time to generate the processing test bench, right? And then if you have to find somewhere to copy a similar test bench for a similar circuit, is for example the asynchronous tutorial that you have in P5, okay? Down there in the testing, you have a very similar circuit, you know, 2 waveforms, the clear direct and the clock as inputs, and then the Q, which has to be monitored, right? So the counter 4-bit async test bench is where you can find, you know, something to copy and adapt. So let's click here and see, for example, if we can copy the clock period this way. Control C and place it in the right test bench. 10 microseconds, which means that the frequency is 100 kilohertz. And so you may like to run the circuit for, well, for example, 300 microseconds. So now it's time for deleting the always and the init processes and make room, as usual, for copying the activity from the stimulus process that you see here in the web, which is the clock process, Control C. In one hand, for example, a square wave, clock period half being 1 and clock period halves being 0, and then the other process that you can call very well a stimulus process, as you see here. This time is very short because there is nothing to say. So basically an initialization period of 100 nanoseconds or something, and then the clear direct go next, and that's all, because there is nothing else to drive here. Okay, right, so in the end, after the functional simulation, you can see the wave, and the wave looks like that, just like this way, you see. In some way the system is not initialized at the beginning, then you are asserting the clear direct to 1. Now is when the system is initialized, and the initial value, because of the connections, is 0, 1, 0, and then you have the opportunity, the system generates 0, 1, 1, 0, 0, 0, 0, 0, 1, and finally 1, 1, 0, and it is like that, and do not changes at all, never, right? So this is the expected result, and I guess that this is exactly what you got from Proteus. So now the only thing left in this exercise is to take and to analyze it by hand, to see if you are capable of understanding how to start the simulation by hand and generate such a waveforms, because you know this is what is expected for you to develop in an exam, you know, analyzing a circuit like this, not by the tools, which this is what you do at home or in the lab, but by hand. So you see, now you know that the circuit is going to be like that. So now just put all your attention to the problem, solving it by hand, as it was stated in this, list of, and this presentation, of the 3 methods. Now you've got the solutions from Proteus and the solutions from VHDL. So now, well, if you like, you can go to the gate level and inspect a little bit more, with more detail, what is going on with glitches and things like that, due to the idea that you have several clocks here. But, well, now is a good time for you to go and develop the exercise using pen and paper, right? So that is all. Thank you. Okay, what you see here is the same circuit, but from the perspective of the gate level simulation in the end, the step number 5, right? You have the full picture of the, zoom it all, and then you see in the real thing, when you still have not said anything about the CD, the system is generating waveforms. Well, so those waveforms are not important, so you have to wait until you are clicking the clear direct. So this is the time when you click the clear direct, and now is when the system starts with the initial combination 0, 1, 0, right? And then if you've got the system with this CD high, nothing happens, because the digital system, whatever it is, synchronous or asynchronous, the digital system is blocked, is in the reset state, if nothing happened. Then when you are switching off this state, when you are deactivating the clear direct signal here, well, now is when the system starts changing states. For example, now you have that it goes from the 2 to the 3, and then the 0, and then the 1, and then the 6. That's right. Okay, so look at this. Let's focus now in a given transition, right? This is the This is the state 2, the initial one. This is state 3, and then you have a new clock, and it looks like that every time that you have a new clock. All right, every time. Well, there is here this annoying, you can switch off these vertical lines which are not locked to the rising edges. You can get rid of this in this way. Display the grid period count. I think that is this. Yeah, get the grid out of here, right? Like this. Now it is better. You have a cursor in this rising edge in this rising edge of the clock, and another one here, for example, right? Two cursors in this transition, and here you are 001 and then 110. So now if you go zooming, because it's a gate level, you can pinpoint what is going to happen here in this transition of the clock, right? So you can go like that, and now one of the cursors is kept in the rising edge of the clock, and the other is kept in the output. You see, every output goes in its own way. So in the end, it happens that the input clock is like this, and the system is generating different codes in between. You see, this is the initial code 0, 0, 1, and then what is expected is 1, 1, 0. But in between these two codes you have the code 0, 0, 0, and then even this one here, which is the 1, 0, 0, right? So this is what happens in these systems, and you can appreciate that here. You can watch this thing here in this gate level simulation. All right. So in this example 5.4, the full sequence to be considered is that one, when the system is with a 1 in the clear direct, you've got the 0, 1, 0 code. We may say that that's the 2. Then you have the 0, 1, 1 for one period. And then you have another period where you have 0, 0, 0, and then 0, 0, 1, and finally 1, 1, 0, and that's all forever. The system do not change anymore unless you reset again, because you see, when you reset again, you will have the same burst of states: a 2, a 3, a 0, and a 1, and a 6. This is what the system is going to do, right? And if you go zooming to a given or a specific location, like that, you find something like this here. All right. Just zoom a little bit more. Like now. Yes. So here, before you can capture the screen with the snipping tool. No. Because the snipping tool is yet active, so okay, now you see the code before the rising edge of the clock. You see the 0, 0, 1, and in the end it has to be 1, 1, 0, but in between you have the code 0, 0, 1, which is kept up to this point, and here one output is changing, the output 0 changes the value, so you have 0, 0, 0, and then you even have this other one which is 1, 0, 0, which is the 4, right? So that's what happens in this period of time that goes from the rising edge of the clock to the final setting of the waveform. So here you have a a period of time of 9.7 nanoseconds, and in between you have these two intermediate codes which shouldn't be here, right? And this is because the signals are propagating from the clock to the cues, right? So that's kind of a final exercise about analyzing the waveform from the gate level simulation. And finally, if you like to inspect the timing analyzer, you see that from the first chip clock, to the output, it takes 3.7 nanoseconds, and from the same clock to the other output, for example, the Q2 or the Q1, it takes more or less double that, 7 nanoseconds. So, and this is because the system is not synchronous. You have to go adding delays from one flip-flop to the next, because the next clock which is triggering the next flip-flop, for example the chip 2 and the chip 3, the two flip-flops that goes after the chip 1 are triggered once the Q is settled after the propagation delay of the chip 1. So you see, this is really a complication. So this is why now you can imagine that in this transition you have, instead of 3, 0.7 nanoseconds, you have 2 times that, right? Or even 3 times, because it's that way, It's because it's an asynchronous system and not very reliable at all. So this exercise is for just showing you that mess that generates these kind of circuits. They work in some way or another, but they are not consistent or reliable, and we will reject that kind of circuits from the next projects, right? All right, so let's see if we can do something about the handmade analysis of the circuit of the problem 5.4, right? It is something like this. You can sketch it with a pen in a sheet of paper, and the way to start is just generating the clock. You are selecting a color, so you can have a paper with a grid like this, so you are going to be sure that every square is a period. That's one way to do it correctly, right? So every one of the squares is just a period, whatever the shape. It's not that important here, because the most important thing here, is the rising edge. So you've got some pulses. This is going to be the clock, and then it is necessary to start the circuit with a given pulse from the clear direct. This is you pressing a button, and this is going to last several clocks, and in the end you are not going to do that any more times. So in time you've got these two signals, and then what? Well, then you know that the system will start very well after the initial clear direct. So you have to pay attention now in how many inputs you have to go sampling. All right? So for example, one signal that is going to be switching because of the connection, is that J0, this one is going to go switching. All right? So here, naturally, you have to have the J in time, because this one is going to go switching. J0, if you like. All right? Then this one is going to be sampled all the time to be 1. So if you like to represent it, is okay, but it's not that necessary. But the other one, the J3, you see, well, if this is the J0, this has to be the J1 to make it easy, right? So the other J that is going to be sampled all the time is going to be the wire W, because it's connected to the Q of the chip 2. So this one is going to be sampled. So you have to make room here to represent as well the signal, okay? So this is going to be the J2, but you can annotate it here, or you can do it in another way, right? If you have the J1 and you have the clock, at least an initial value, because this J1, it is going to be the Q0 that you've got from chip 3. You can imagine which is going to be the value of this signal, okay? So perhaps before annotating or representing the J2, okay, it is going to be better to represent the Q0 and then the Q1, okay, which is this J2, and then the Q3, so something like this, right? So Q0. And another important signal that you have to consider, naturally, is the Q0 naught, because it happens to be the clock of the next two stages, right? So this is really very important to represent. It is going to be Q0 naught, all right? And Q0 naught, it may have a good name, for example, clock 1. You see, in this way you have one clock and another one which is applied at the same time to the two flip-flops, chip 2 and chip 3. So this Q0L is going to be the clock 1. But you cannot represent it now like the clock 0, because this clock 0, this initial clock is external. You drive it, but not that one. That one is going to be generated internally when the output Q0 is switching, you know. So the next signal that has to be taken into account here is the, you know, the J2, which is the output of the second chip. So this is for you to represent yet another signal here, okay, in time. And this time is going to be the J2 or the Q2, which is the same, right? And then, you know, if you've represented the J2, which is going to be sampled by means of this clock 1, you can go and represent the last one, which is the Q3, which at the same time has the name W3, right? And the Q2. Well, no, it's not Q3, but Q2, right? So you can just do it correctly. There's no need to invent another name here. It's that Q2, right? So now it's time for you to represent yet another signal in time. And this is finally, well, wait, because the J2 is not the Q, well, it is J2, right? It's not Q2, because the Q2 is the one which is the chip 3, you see. So take it easy, and this is the wrong level here. Okay, the J2 is not the one that is going to be an output. Be careful, right? So before representing anything else, like the Q2, you better represent the Q1 as the naught of the J2. That's the point. So this one, yes, has a good name, which is Q1, which is, you know, J2 naught. And then there is time for you to represent the next one that way. And the next one, it is, yes, this time, yes, Q2, which is the W3, right? And this is the signal that goes to the output as well, and goes as a naught to the initial value of the J1, all right? Okay, so this is the layout that you have to, you see, it's a full sheet of paper, basically. That's the starting point. Takes time, I know, but that's the way to do that, because it is about thinking about all the circuit together and the like. So the way to start now the analysis is by means of the clear direct signal, naturally. But before doing this, we very much go and mark the important times, at least for this chip 1, which are the ones that we know very well. So you can now get another color and mark, not to the end, you know, be careful with this, but now pay attention, because I will mark here. This is the first one that has to take into consideration, right? But down to the Q0 and Q0 not only. You see, this is valid only for the clock that you apply externally. So you can go like that, because this is, yes, the first rising edge, and the second, and all of them, right? So, but be aware of this. You are marking vertical lines, you know, instants of time that do not go the same for all the flip-flops. Be careful. The ones that you are marking here in red attain only the chip 1, right? So then what goes next? Well, the clear direct, all right? That is what goes next. Here you are generating a clear direct. So before this clear direct, that you really can go to the end. So this is true. You see the difference? This clear direct is applied to everything here, all the flip-flops, so it goes to the end. So now, because you are marking outputs here, you see the Q1, the Q2, so all this is output. So whatever it is before this time is unknown. You can write the diagram like this now for every single output, because even it is this, the G1, you know, the G1 is nothing but the NOT of Q of the chip 3. So it is an output, and because it's an output, is unknown. But now, for all this period of time in which you have the clear direct applied to the system, and a little bit more, because you see, here you are deactivating the clear direct, but the system will remember at least up to this point. So all this time, you know, what? Well, which one goes first? The Q0, right? The Q0 goes first. So Q0 is 0, like that. Okay? And then the Q0 not goes high, so it's 1. The J2, which is nothing but the Q of the second chip, has the same idea. It is 0. But the Q1, the output of the system, which is the J2 not, goes high, right? So, like this. So take it easy, because this is small. You have to do that step by step, taking care about everything here, just thinking about it all. So now what goes next is the Q2, right? So the Q2 that you are representing as this input has to be 0. All right? And what else? Now, finally, because this is 0, you can print this one here with a 1, because you know this is the NOT, you see. J1 is not. This one is a NOT. Q2, right? So every time that you're defining the Q2, the Q2 NOT is the one that is applied to the system. So you see now what happens. Well, you can work only with the first one, because the second one is going to work once this output Q0 has been fixed, but not before. So now is your turn to fix the Q0. In which way? Well, this is the time in which you are going to sample this value, right? So you are sampling a 1 here, which means that because key is 1 the same, right? So this means that you will have at Q0 the opposite value or not. So now it's time for this to go like that. You see? So you have to have a 1 now in Q0. All right. So what else? And because this goes from 0 to 1, the QL goes from 1 to 0 at the same time. You may imagine like this. So now you have a 0 here. And the others, what? Well, the others, nothing, because they don't have the right, they are driven by the clock 1, and the clock 1 is not yet with the rising edge here. So you have to keep the other signals as they are for at least another period. You can do nothing about the other signals, but they have to wait. They are saved. Okay? So now so you see this one, which is important here, J1 is kept high for at least another period, and now is sampled again, because this is the next clock. And now what happens? Well, because you have a 1 and a 1 in the key, you are switching this down for another period. So this is a 0, and this is going to be a 1 for a full period of time. Then what? Well, now you've got here something, and this something, you see, is a rising edge. But be careful. So this is what you have to do now. You have to delete in some way this rising edge and mark it slightly apart from the vertical line in red, because it is like that. This is a rising edge, which is going to be important because it's the clock 1 for the 2 remaining flip-flops. So now, because you've got here a rising edge, the J2 is sampled. So it's sampled here, slightly separated. So you see now you have a vertical line which is right to draw, because now it is when you are sampling the J2, and what else? You are sampling the T, but the T is always 1, so it's not a point. It's not necessary to be representative. You know what happens here when the T is 1. So if you've got a rising edge in the clock 1 and T happens to be 1, the J2 will switch, which is what happens here. You see, you have a 0, and now this is going to go 1 that way. All right, and now because the Q1 is just the J2 naught, exactly, the one that you see as a port is just this one naught, you see, now you have a 0 here. And what now? This H applies as well to the third flip-flop, and here you have to be careful. You see, the third flip-flop is sampling, because it is the same clock, this value G2 at the same time as this one here is sampled, okay? And this means what exactly? That this is sampling J2. So what is the value that you are going to sample? A 0, right? So you can color that in a different, like a 0. You see, you are sampling a 0 here. All right? And because you are sampling a 0, okay, and this is 0, 1, and this is a GK flip-flop, nothing is going to happen. You see, 0, 1 means that the system is going to keep the value that it is already a 0 here, right? So this clock is not going to change this value. So now you come back to the black ink. So because of the 0, you know, this one is not going to change. For a full period of time. So now, because you've got a 0 here, you are sure that the J1 is 1 again for a full period of time. That way. And now you've got another rising edge from the principal clock, the main clock. Now you can go and sample this 1, and you know that is a 1, the same as before. So now you can switch the Q0 and the Q0 naught as before. This is going to be a 0. And now what? J2, what is going to happen with the J2? Well, you do not have a rising edge as like this. You have a falling edge, right? So the falling edge is not going to allow you to sample the J2 in any way. So this value is going to be kept. I mean, nothing is going to happen if you have a falling edge as the clock, right? So this one is going to be kept another period of time. So if this is kept high, this is going to be kept low, like that. Okay. And so if this is kept low, okay, G2 low, now you know that because you are not having that one is the same as the other one, the 3 is the same as the 2. So if nothing has happened in the J2, nothing has to happen in the Q2, because it's the output of the chip 3 that is driven by the same clock. So if nothing has happened here, you see, you keep the value, this one has to be kept the same, 0 and 0. So if this is 0, you have another time for another clock, another one up there. All right, and this one now is sampled again. Okay, so if you've got this value here, now because it's 1 and 1, you switch this down again and you switch this up. And now you see you have the same as before, another rising edge in the system, which is going to generate another vertical line that is going to be slightly different from the red one that you do not develop to the bottom. And this is the time in which the second and the third flip-flop will evolve, if that is the case. Okay, so let's see. Now you have a rising edge. This one is sampled. Well, you sample for the third in the chip 2 you are sampling a 1, so naturally this will switch the J2 now, which is the Q. The J2 is going to switch here specifically to become a 0. Okay, and so because this is the opposite value, you will generate a 1 in the Q1. And finally, because the next one is the same thing, and you know here you are sampling a 1, you see this one here is going to make possible, you know, that this one goes high. Okay, because you have a 1 in the J2, here you have a 1 and a 1 in the K, so 1 1 means that the chip 3 is going to switch. Okay, this wire is going to switch from what? From 0 finally to a 1. At this time, you see, is slightly different from the red vertical line. There is this delay that is making this kind of a messy thing. So now, because this goes high at this specific time, you see just some nanoseconds, this one here, G1, is going to go down just a little bit later from the red line. And now you have a 0, the remaining period. And now, you see, the next time that you are sampling this, here, you will sample a 0. All right, look at this. You are sampling a 0 now. And if you are sampling a 0, this is a 0 in the G1, and this is a 1 in the K and a 0 in the G1, so this makes it possible that the Q0 is going to be kept as it is before. It's not going to switch as the previous period. Is going to be kept for another time the same, right? So look at this, how tricky is this thing at all. So now you have another period, the same value. And that signal is important because the opposite of this signal is what you see as a Q. Q0. No, the opposite of this signal is what is going to become the clock. So you see, there is no variation in the clock 1, right? It's something like this. It is 1. And so, if this is 1, what? The G2 is going to be kept. The same value 0. And the same for the Q1. And the same for the Q2. And now, I guess that if this is 1, well, this one here, J1 is going to be 0. And now you see you have another period and you are sampling another time as 0. And this is going to make the things the same as before. If you are sampling a 0, the Q0 is going to be kept as it is, because it's the GK flip-flop that is doing nothing at all, keeping the state. And so Q0 not, and so G2, and so Q1, and so Q2, and so finally this one. So you see you are very well sampling again a 0. So it looks like that everything is going to be the same all the time. All right, you can go now and imagine that nothing is going to change because that's the real thing. But you know, if you like, you can imagine this in the end like this. You can imagine that someone clicks the button clear direct again, just to show you that you can start the machine again, you know. So if in the end you delete a little bit of this thing, well, not that much, you know, you can generate in blue the clear direct from this point, and you see sometimes later, anytime you like, you click another time the clear direct. Okay, so what is going to happen now? Well, if this happens, you are, in this case, you have to mark exactly the time when the things went like that, you know, when you click the clear direct to the bottom. So now the signals are going to change naturally. If these signals has been stable forever, you know, many clocks now, thousands of them is necessary. Now at this time everything goes as if it was the beginning of the problem. All right, and what is the meaning of this? Well, it means essentially that the Q0, if you pay attention to the Qs, because this goes fast, the Q0 goes 0, no problem. And this is up to this point when this rising edge is going to take meaning. Okay, so you have a 0 here. Then the Q0 not have a meaning of a 1, and then the J2 the same thing as before. So because the J2 is the output of the chip 2, it has to be 0, you know, because it's reset, at least up to this point. Then we will see. And Q1, because it's J2 not, has to be set high. And finally, the other chip is reset the same. So if this is reset, sorry, because I did it wrong, this signal, you see, I have to do it like that. From now on, it goes down to 0. Now it's correct, because it's the output, Q2. What is 1, you know, if this is 0, what is 1 is this signal here. So J1, you know, goes high, and is kept high up to this point when you sample, and now you sample a 1 in this signal, and so you can go and evolve the circuit in the same way. Just a last turn in the last period to see that you get the same thing as you are expecting, right? Let's do it again, one more time. If you are sampling a 1 in J1, you know, this means that now, not as before, you know, that you were sampling many times zeros, now you are sampling what? A 1. So 1, 1 means that the Q0 is going to switch in this red vertical line. So you have a 1. This Q0 naught is going to go down, 0. And, well, if this is the clock 1, nothing is going to happen here, because there is no a rising edge, but a falling edge here. Is that right? So, good. So, Q1 is going to be kept 1, and this is going to be kept 0, so you know that the next clock you will sample again another 1. So now you can recall this long explanation of half an hour, you know how long it takes. So you can recall it now and looking at it from, you can see the full picture and you can see what is going to be the output, you know. Let's see, the output is going to be Q, 2 down to 0. So let's see, because before the clear direct, it's not important, but when you apply a clear direct, you have a clear code here. Which one? Now is when you can take a different color and mark what is going to be the output. Let me see if I find a right color. For example, Q0 is what is going to be a value, so 0, right? So 0 here, then another thing that is going to be an output, another signal is the Q1, which was that one here, right? Q1 is going to be another output. And finally, Q0. So what is the code that you've got here? Q2, 0, 1, 0, I guess. So while the system is in reset state, you have the 2. Then what? Well, there is this first change here, you see? So the Q0 are going to change. So you have something like 0 now, 1, and 1. So this is going to be the number 3, I guess. 0, 1, 1, right? Q0 happens to be 1. So this is the number 3. So you see the system has changed from the state 2 to the state 3. And now what goes next? You see you have a 0 and a 0 and a 0. You see 2 signals changes at the same time. So you happen to have 0, 0, 0, right? It looks like that. So 0, in this period of time here, you have 0, 0, 0. So from the 3, you jump down to 0. No, not like that, because it's a number. And then the next period of time, you know, another full clock, you can say that you've got 0, then what? 0, and finally another 1. So what is this number? The number 1. So you have 0, 0, 1. So from 0 you jump to 1. All right? And finally, you see, there is a state which is the definitive one, the final one, because it is not changing unless you are applying here another clear direct. Okay? So if before you do that, reinitializing the machine, the system has no more switching, you know. It has a final position, and this final position happens to be 1, 1, all right, 1, 1, and then Q0, which is 0 all this time, you see. So this is the number 6. So that's it. This is what the machine does, you know. It's a kind of a special counter. A burst, you know, it generates a burst, you know, a single signal. It's not periodical or anything like that. It's a burst, you know, and the machine supplies the numbers 2, 3, 0, 1, and 6, this combination, and then the 6 is kept until you repeat the same sequence, 2, 3, 0, 1 and 6, and that's all. This is what the machine does, right? You see? So that's the final analysis, and this is what I like you to do for the given circuits A, B, C, D. All right. So, good. Okay, I forgot, before finishing this tutorial, this recording, well, we have to be sure, or more or less, that if this is the same thing that you got in Proteus and the same thing that you got in VHDL. So I hope so, right? So the machine starts in 2, then goes to 3, 0, 1, and 6, by means of the 3 methods. But, you know, in the final gate level simulation, the things went different, because we were pointing on one of these. I remember we were just zooming in one of these transitions, and in between we get different codes. I remember that between the 1 and the 6 we were able to see the 0 and the 4. The 4, for example, that do not exist here. So this spurious code that was the 4. You know, you get between the 1 and the 6 a repetition of the 0 and then the 4. So you see, that's the kind of thing that do not have to happen in the real circuit. You may like to have this sequence 2, 3, 0, 1, and 6 for any reason or any application you may imagine. But you know, what is not possible is to have in between, for even a brief period of time, something that is not expected, like the number 4. So that is why we are not going to go like that nevermore, right? If we have in mind to invent a counter like this, that has a special burst of signals, 2, 3, 0, 1, 6, naturally we'll be able, that's a good thing, to finish this project 5, you know, the things end in some way like this. We will clearly be able to design this chip, burst generator that generates this special sequence, you know, 2, 3, 0, 1, 6. We can do that very well the next P6 and the next P7 using synchronous counters and using finite state machines that will be 1,000 times easier. You're nothing like that anymore. So this is only for you to learn about the intrinsic way, the specific and detailed way in which the flip-flops work, especially when you have several clocks in the same circuit. That makes you go through a project that is very, very complicated, right? That's all.